I'm going to the moon because I can't stay here on Earth. Okay, so when we're talking about elastic potential energy, we're really talking about energy that is stored, or the energy of position, of something like a spring or maybe even like a rubber band. In fact, there's a lot of stuff that we can kind of categorize as like an elastic type object. But really, whenever we're talking about this, we are talking about anything that can go back to the beginning of the year and use our spring equation. One of the equations we learned early in the year, also known as Hooke's law, was the spring equation, where that the force to either stretch or contract a spring was equal to this. So it should be equal to this force, and this force equals, for Hooke's law or the spring equation, a negative kx. Where, as we talked about earlier in the year, this k is some sort of spring constant. It's like how hard it is to crush or like compress a spring, or how hard is it to pull a spring apart. You know, whenever you're clicking your pens and pencils, those have small spring constants, so you can do that with a thumb. But like the springs on your car are much, much stronger, much bigger. They have much larger values of k. This x here, that represents how far you have stretched or compressed that spring from its equilibrium position, so from where it's at rest. And this negative is just implying that whichever way you stretch it, the force is acting opposite of that. So if you took a spring and you stretched it out, it wants to come back. If you took a spring and compressed it in, it wants to go back to normal. Okay? So that was just our force equation. This was Hooke's law. Now, in terms of elastic potential energies, because they're still potential energies, we're still going to use that capital U to describe them. And then some people like to use the letter E for like an elastic potential energy. I personally like to use the letter S, because I always think of these as like springs. So like a spring potential energy. But if you want to use UE, US, nobody's going to yell at you for that, as long as you know what you're talking about. Now, a kind of interesting thing about this spring equation is the spring equation actually will get us to a potential energy equation. And the reason being is as follows. If we go over here and make a little graph, this is our force displacement graph. We know that the area of this graph is equal to some work, which we can think about in terms of an energy. Well, if we plot the spring equation, F equals kx, and we're going to ignore the negative because that negative just means some direction, which we normally draw in our free body diagrams. So if we just plot this slope here is k, because that's the spring constant. Well, what this means is that if I wanted to find how much work did it take to stretch this spring, how much energy did I have to put into the spring, or how much potential does the spring currently have, well, all I need to do is find the area under the curve. And because this is a nice right triangle, I know that the area under the curve is equal to 1/2 multiplied by a base, which this is just stretching the spring some displacement. This is just some delta x here, right? So this is like 1/2 times the base, which is just x, that's just our displacement, and then multiplied by the height of the triangle, which is just some force. Well, how much force does it take to stretch a spring out to this position? Well, we know that. It's this equation, F equals kx. So if that force equals kx, we can come over here and put kx into this equation. I've omitted the negative because that negative is just a convention of, what direction is that force acting. I only care about the amount. So what this does is, while this is equal to the work, if that's work that I've put into the spring, I've stored that energy in the spring. So this gives us quickly that the spring potential, or the elastic potential energy, is equal to 1/2 k, and these x's get multiplied together, so we get x squared. So all we did is we used a force displacement graph, found the area like we've already done, And with that idea, we quickly find that the potential energy of a spring, or an elastic potential energy, is this 1/2 kx squared. And this is the equation combined with Hooke's law, or the F equals kx equation, that we're going to be using to solve our problems out here. So in our example here, what we're going to be looking at is this example problem for an elastic potential energy. We have a rubber band, ta-da, and it's stretched 0.15 meters by a force of 12 newtons. We need to calculate three things: the spring constant, the elastic potential energy at the position of 0.15 meters, and then the elastic potential energy when we stretch it to 0.3 meters. When we do these problems, part A is arguably the most important, because you need to find the spring constant first. You cannot get the potential energy without knowing the spring constant, which we don't know. We just know how far it's stretched and what that force is. So what we can first do is we can find the spring constant. We can say that, look, a force is equal to a spring constant multiplied by some displacement. I've left out the negative here because it doesn't matter. The negative was nice for our free body diagrams in Unit 6 when we were talking about forces. In our case here, I don't care what direction we're stretching the spring. It's just being stretched. And then with this equation, this Hooke's law equation, we can just solve for k. We can just say k equals F over x, which means when we put in some values here, we get 12 newtons divided by 0.15 meters. This will give us a spring constant. Okay, so crushing these numbers, 12 divided by 0.15 is, whoops, that's wrong. Learn to type, is a spring constant, K, equaling 80 newtons per meter. That is our spring constant. We needed to find that. If we didn't find it, well, we're going to be wrong. Pew! Now that we have this spring constant, we can find our elastic potential energies. We know the equation for this is going to be 1/2 kx squared. So if we just take our values that we have and plug them in here, we're going to have 1/2 multiplied by 80 multiplied by x, which for part B is 0.15 squared. Please be aware that only the 0.15 is being squared. Only that 0.15 is being squared there. So whenever you're typing these in on a calculator, I like to start with the 0.15 squared first, and then multiply and divide by everything else. So 0.15 squared is 0.0225. It gets smaller because we're multiplying a decimal by a decimal. And then we multiply by 80 and then divide by 2. And we find that our stored energy here is going to be 0.9 joules. And it has to be joules because joules is our unit of energy. Now for part C, we're doing the exact same thing. But this time, we're not stretching it 0.15, we're stretching it 0.3. So if we wanted to, we could, write out the same equation, 1/2 times 80. Note, the spring constant, this 80, it does not change. Once you find it, that's what it is. The spring doesn't change just because you stretched it further. It's the same spring. It's the same rubber band, whatever it is. So the spring constant is still going to be 80 for us. What does change is how far we stretch it. Now we're stretching it 0.3, and then we need to square that. If we want to, we could rush this through our calculator. But this isn't bad mathematics to do, considering that we are just stretching it twice as far as before. Now, here's the puzzler. If we stretch this spring twice as far, will our energy double? Will our stored potential energy double? That's the question. Think about it, and then come back to me. In our case here, when we double this stretch from 0.15 to 0.3, that's double. Not only are we doubling it, but we are squaring that amount. So 2 times as much, but what is 2 squared equal to? That is 4. This will give us 4 times as much energy. And 0.9 times 4, or like 9 times 4, that's going to be 3.6 joules of energy. And if you threw that into a calculator, you'd get the same thing. If we stretched this to 0.45 meters, this wouldn't be 3 times as much as 0.9. It'd be 3 squared, or 9 times as much. And we'd get 8.1 joules. And this is because as we stretch that spring or that rubber band further and further, it gets harder to stretch it further, which means that we're putting even more energy for that little bit extra at the very end. Okay? So be aware of that. This square is very, very important. That really starts expanding out how much energy we store into a system. And that's why if you're snapping a rubber band or a spring on someone, pulling it back just a little bit further isn't just a little bit. It's a little bit squared. So it's really a lot more, and it becomes a lot more quickly. Okay? So be careful about that if you're playing around with springs. One spring you should really not play around with unless you really know what you're doing are garage springs. Garage springs are high tension springs. There is a lot of stored potential energy inside of them. They have been known when people don't know what they're doing and they unfurl the spring or they snap it, they can cut arms off. They can shoot and then go through a cinder block wall. Do not mess around with your garage springs. A PSA to everyone out there. Don't mess around with them unless you are a professional garage door mechanic. It's not worth losing a hand or an arm or your life for a little bit of money to pay a professional to come on in. Please be careful around your garages, okay? There is a lot of stored energy inside of them, and you don't want to be on the receiving end of that, okay? But this is our little example here. What we're going to see next is a practice problem for that, but right now we are finished here. Until next time, stay safe out there, stay away from garage doors, and adios, and take it easy.